All right, welcome everyone. Today we're going to look at another one of our series tests. This one is called the comparison test, and we're going to see how to use this comparison test to show that a series is either convergent or divergent. All right, so let's get into it. And the motivation behind, we're actually going to see two comparison tests. So there's going to be the comparison test we look at today, and then there's another one which we call the limit comparison test. And essentially the idea behind both of these is that we compare a series which we don't know whether it converges or diverges. So we have this series with unknown convergence, and we're going to compare it to a series that we actually do know. So here in this kind of little example here, we have this series formed from 1 over 3 to the n plus 1. We don't know if it converges or diverges. But what we're going to see is we can relate this to a series which we do actually know something. So here we have the series 1 over 3 to the n. This one's a convergent geometric series. So we're going to see how to actually use what we know about this series to actually tell us what's happening with this unknown series, this series with unknown convergence. All right, so let's get into it. So we have our test, our comparison test. So we suppose we have our series sigma an, and we have another series sigma bn, and these are two series with positive terms. So all of the terms in our series are positive, greater than 0. Now what the test actually says is that if sigma bn, our series formed from bn, is convergent, and we have this inequality where the terms an are less than or equal to the terms bn for all n, well then our series sigma an is also convergent. So if sigma bn is convergent and this inequality is true, then sigma an is also convergent. And it also works for divergence. So if sigma bn is divergent and bn is less than or equal to an for all n, well then sigma an is also divergent. So, a little typo here. If we have a series which we know is divergent, and we have this relationship, bn is less than or equal to an for all n, well then our series sigma an also is divergent. So this comparison test can be used to show both convergence and divergence. And so in this, what this test actually says, we have these two series, sigma an and sigma bn. And so in each of these, sigma bn is the series which we actually know what's going on. So this is our series where we know whether it converges or diverges. And sigma an, that's our series that we're actually testing. This is sort of our unknown series. So this is our unknown. Sigma an is our unknown. All right, so how can we remember this? How can we remember this result? Give a little motivation for why this result is true. So let's start with the case where we have this inequality, an is less than or equal to bn. And let's suppose that we form the sum for each of these using each of these sequences, each of these terms. So let's look at our sum sigma bn, our series formed from adding up all the terms in bn. And in this first case, we know that sigma bn is convergent. So what that means is this sum actually exists. It's a finite sum. And we know that because it's convergent. So what that means is if we're adding up all these bn terms and we get a finite number, well then what happens when we actually add up all of our a terms? If we add up all of our a terms, we should also get a finite number because each of those terms is less than or equal to bn. So if we add up all these bn terms, we get a finite number. Well, if we add up these terms that are less, they should also add up to something, and they add up to, they give us a convergent series. So sigma an is also finite. So it has to be convergent. And the same kind of result works for the other inequality. So if we're looking at this other inequality, so bn is less than or equal to an, and if we try to add up all of our bn terms, so in this case, if we do that, we get, an infinite sum, potentially. And it's divergent. So if we add all of our bn terms together, it just gets really big. It becomes an infinite sum, and so our series diverges. Well, if we try and do the same thing with our an terms, if we try to form our sum sigma an, well, if all these an terms are bigger than the bn terms, and adding up all those b terms gives us an infinite sum, well, then adding up these things that are larger than it must also give us an infinite sum. And so, divergent. So it's kind of a way to remember here. So when bn is larger, it kind of forces our an terms, our series formed from our an terms, to converge. And when bn is bigger and it diverges, well, then it forces our an terms, the series formed from our an terms, it forces them to diverge as well. So we can think of, in this case, sigma an is forced to converge. So these sigma bn terms are converging. It converges to a finite sum. Bn is bigger than an, so then adding up smaller terms must also give us a finite sum. So sigma an is forced to converge, whereas over here, in this case, sigma an it's kind of forced to diverge. It's forced to get bigger and bigger. So we know our bn terms, if we try to add them all together, it produces an infinite sum. Well, our an terms are bigger, so it's just going to be potentially an even larger sum. So it has to diverge. It's forced to diverge. So this is kind of the motivation for how this comparison test, why it seems plausible. By no means a proof, but it seems plausible. So what are we actually comparing? So kind of the tricky thing about doing the comparison test is we have to actually choose this series sigma bn, which we're going to compare it to. So we have this unknown series. We don't know what's going on. We have to come up with a series that we're going to compare it to. And we have to pick a series that we actually know what's happening. So not only do we have to come up with a kind of a comparable series, but we also have to know whether it's convergent or divergent. And so usually what we do is we rely on either our geometric series. So we're going to choose our comparable series sigma bn to be either a geometric or a p-series. And we just have a nice little review of when those types of series are convergent. So our geometric series, where we have r to the power n, is convergent when the absolute value of r is less than 1, divergent when the absolute value of r is greater than or equal to 1. And then for our p-series, it's kind of the opposite. So it diverges when p is less than or equal to 1, but converges when p is greater than 1. So geometric series are kind of related to exponential functions. P-series are kind of related to power functions. Again, we have n raised to some constant power p. So it's helpful to kind of remember these two types because these are the ones that we're, for the most part, going to be relying on. These are going to be our comparables. All right, so let's try looking at Well, we're going to try an example, but before we do, we kind of go through the usual disclaimer and tip where the starting index value doesn't really matter too much for the actual convergence or divergence of our series. And so we can kind of relax the conditions a little bit in the statement of our comparison test. So, and the test still works. So we can relax those conditions, so that we don't necessarily have to start directly at n equals 1. We maybe have to go a little further into each of our sequences, and that's okay. The comparison test would still work. So what were our two conditions? Well, the terms in our sequence, the terms in our series all had to be positive, but it's okay if there's a couple negative terms at the beginning, as long as if we go out far enough, if we go out far enough in each of those terms, eventually they all do become positive. So it's okay if there's a few at the beginning where they're negative, as long as they eventually become positive and stay that way. Same thing for the inequalities. So the inequalities, we saw either an had to be less than or equal to bn, or depending on the other one, bn was less than or equal to an. There could be a few terms at the beginning where maybe these inequalities are not true. But eventually, if we go far enough in, eventually then they do satisfy these inequalities. So we kind of loosely define this word eventually, but it means if we go far enough in, we can find some integer capital N where the terms in our series satisfy these conditions for all index values greater than or equal to that capital N. So, if we kind of write out, sigma an, be like a1 plus a2 plus a3. This is where we're starting with n equals 1, going to infinity. And then maybe we get to an minus 1 plus an plus 1. And it's helpful, again, to think of the tail of our series. That's where all of the really interesting and ultimately where the kind of convergent or divergent behavior, where it actually happens. So when we're writing out the terms of our series here, the convergence or divergence really happens on the tail of our series. What happens when we keep going? The first few terms at the beginning, those don't affect the convergence or divergence. So these terms towards the beginning, it's okay if some of these are not positive, or it's okay if some of these terms here don't satisfy the necessary inequality. It's just if we go far enough, then we hit a point where the terms actually do satisfy those conditions, and they all satisfy them. We can use the comparison test then. So it's okay if there's a few terms at the beginning that don't quite satisfy everything. We could still use the comparison test as long as there's a certain point where then everything is met consistently. All right, so let's try an example. Let's look at example 1. We're going to use the comparison test to determine if this series is convergent or divergent. So it's the series sigma n equals 1 to infinity, and it's 1 over 3 to the n plus 1. So the first step is we actually want to find a series that we're going to compare this to. So we want to find our comparable. What's our comparable series? Well, we call this sigma bn. And the way to kind of identify it is kind of just to look at the dominant terms. So look in your fraction. A lot of times we have a fraction. Pick the dominant term in the numerator, pick the dominant term in the denominator. So we're looking for the dominant terms. So in this case, our numerator is a constant 1. So I'd pick 1 for the numerator and then that 3 to the n in the denominator. So that plus 1 is really kind of the what's making this, unknown. We don't really know what's going on here. But we suspect that the dominant term is really going to ultimately influence the behavior of this series. So we're going to compare it to the series sigma bn, where we're using 1 over 3 to the n. So we just identified the dominant term there. And writing this is a geometric series. So this is convergent. So this is a convergent geometric series. And what's the r value? Well, r is equal to 1/3. And then we just state that the absolute value of r satisfies the necessary inequality for this to be a convergent geometric series. So it's a geometric series. We know it's convergent because the r value is 1/3, which happens to be, when we do the absolute value of 1/3, is less than 1. So how can we actually see? Maybe we don't quite see yet that this is a geometric series. So we could, if necessary, we could rewrite this as, if you're not convinced yet, you could go through our usual exponent some of our exponent properties, where we think of there's a hidden exponent of 1 here on the, or n here on the 1. So we could really factor off that common exponent. So we could rewrite this, if you're not convinced, as the sum from n equals 1 to infinity of 1/3 n. And so now we do see that kind of general r raised to the power n form. It's a geometric series. The r value is 1/3. All right. So that's kind of the first step, is figure out your comparable series and then state whether it's convergent or divergent. Normally we're doing either a geometric or a p-series. All right, so now we want to go through and actually show the necessary conditions. So this is kind of the second part. So first part is find the comparable series. The second part is go through the conditions. So there's really two conditions for our comparison test. We need all of the terms in sigma an and sigma bn to be positive. So if we look at this, yeah, everything's positive. 3 to the n is positive. The 1 in the numerator is positive. When we divide two positive numbers, we get a positive. Over in sigma an term has this plus 1. Again, that's positive. So everything here is positive. So we need all of our an and bn terms. They're all positive. And again, sigma an, this is the series that we don't know. That's the one we're testing. Sigma bn is the one we do know. But it turns out all the terms here are positive. All right, so the other thing we need to show is that inequality. And since sigma bn we know is convergent, we know it's a convergent geometric series, we suspect that sigma an is going to converge as well. So that means when we actually go show the inequality, we have to show the right inequality. And so for convergence, the one we use is an is less than or equal to bn. This is the inequality we have to show. And the reason why we use that, if we go back to our kind of the statement of our test, we have two potential inequalities here, and we have to use the one when sigma bn is convergent, because the one we're comparing it to is convergent. So this is the inequality we're going to try. All right, so let's try it out. We want to show an is less than or equal to bn. So there's a couple ways to show that an inequality is true, but usually a nice kind of easy way to do it is to start with what you want and simplify it until you get to a point that is clearly true. So let's try it here. So we're going to start. What is an? Well, that is 1 over 3 to the n, and our plus 1 is in the denominator. We want that less than or equal to 1 over 3 to the n. And because everything is positive here, we can really cross multiply, and it doesn't change the inequality. So if we take the 3n, multiply it on the left, well, we're really multiplying both sides by 3n. So when we do that, we get 3n now on the left. And then we can do the same thing with the other denominator, multiply both sides by 3n, 3 to the n plus 1. And here we get 3 to the n is less than or equal to 3 to the n plus 1. And that's clearly true because we have the same quantity that shows up on both sides, but on the right side, we're adding 1. So this right side is clearly more. So this is clearly true. And since this inequality is true, it means this inequality is true. So check. That other inequality was true. AN is less than or equal to BN. And we maybe just qualify that for all n greater than or equal to 1. All right. So that's really it. We have our comparable series. We've shown the two conditions are met. And then really the last step is just to state our conclusion. So the series that we were interested in is convergent. Since sigma Bn is convergent, you know what? And we'll put the convergent there. And then we just state the test that we used by the comparison test. So we clearly stated our comparable series, gave a good reason for why it was convergent, went through and showed our two, or at least stated our two conditions, but the inequality generally takes some work. A lot of times showing that the terms are positive, that's pretty clear from just looking at them. But sometimes the inequality takes a little bit of work. So we showed that. And then that's enough to say, well, since those two conditions are met, and we know sigma Bn is convergent, then sigma An is convergent as well by the comparison test. All right. So that's really it. So it's those kind of 3 steps. So let's try another one. Example 2. We're going to determine if this series is convergent or divergent. Now, what series are we going to be looking at here? It's sigma from n equals 1 to infinity of 3 over 2n squared plus 5n plus 1. Now, technically speaking, we could probably do integral test on this, but trying to integrate this function might be difficult. So technically, a lot of times for these series, you can do multiple tests, but sometimes one is going to be easier than the other one. So probably with this one, we probably could get away with integral test, but we'd have to probably try some partial fractions. It's going to be much more involved, the actual integration. So instead, we're going to do the comparison test. So first step, so we're going to call this just sigma An. This is the one we're testing. And the first step is to actually find our comparable series. What are we going to compare this to? So we call that sigma Bn. And the way we do it is, again, kind of similar. We're looking for the dominant terms. So the dominant term here in the numerator is 3. Dominant term in the denominator is this 2n squared. And there we go. That's going to be our series we're going to compare this to. Now, why is this convergent? Well, this is convergent because it's a constant multiple of a p-series. And what is the p-value? Well, the p-value is that power. So it's power 2. It's p equals 2. And for a p-series to be convergent, what does the p-value need? P-value needs to be greater than 1, which 2 is. So we can see this is convergent because it's a constant multiple of a p-series with p equal to 2. And again, if you're not convinced, we know when we have constant multiples like this, we can actually bring them out. If we know it's convergent, we can bring them outside of the series notation. So we could rewrite this as the series 1 over n squared with the 3 halves in front there. So this actually is a p-series, which we know is convergent, and then we're multiplying it by 3 halves. All right, so that's the first step. Find the comparable series. Next, we actually want to go through and show our conditions. So that's the next portion of this. And there's 2 conditions. Everything needs to be positive. So we want to go through and check. And we're checking this with the understanding that n is greater than or equal to 1. That's where our series is really starting here. Starting at index at n equals 1. I feel like I do that every single time, at least once. So, this 5n could technically be negative if we were doing negative n values. But for n greater than or equal to 1, the 2n squared here is positive. We're adding in a 5n, that's positive. 1 is positive, 3 is positive. So everything here is positive. Same thing for this 3 over 2n squared. Everything here is positive. So for n greater than or equal to 1, an and bn are all positive. All right, so we know that about our unknown terms, and then our series where we actually know that it converges. So that's the first thing we need to check. For the most part, there's not too much to do there. We're just kind of going through. Maybe there's a little bit of, maybe we find a couple terms at the beginning where we might have a negative, but that's okay. In this case, we don't. Everything's positive. Then we want to look for our inequality. So we want to go through and we want to try out our inequality. And if we go up, we have 2 choices for the inequality. We're either going to do an is less than or equal to bn, or bn is less than or equal to an. And how we choose the inequality, which one we need to show, we go up to our comparable series here, and we kind of go with what we're expecting sigma an to do. So if sigma bn is converging, well, then we're going to expect sigma an to converge. And that means we need to show this inequality. So there, you kind of have 2 choices. You have to show the right inequality. So this one is the correct inequality to show here is an is going to be less than or equal to bn. And how you can do this is really start with what you want. So let's start with our an term. This is 3 over 2n squared plus 5n plus 1. Start with what you want. We want this to be less than or equal to 3 over 2n squared. And let's kind of simplify this. So let's multiply both sides by 2n squared. So we're going to get 3 times 2n squared on the left. It'll cancel out on the right. And 2n squared is positive because 2 is positive and n squared is positive. So we can multiply both sides of an inequality by a positive number, and it doesn't change the sign. And then the 2n squared plus 5n plus 1, we can multiply that on the other side. Multiply both sides by that, so we get 3 times 2n squared plus 5n plus 1. And again, that term is positive, so we can multiply both sides of an inequality by a positive number, and it doesn't change the direction of the inequality. All right, so we want to keep simplifying, so multiply terms out. And when we do that, we get 6n squared is less than or equal to 6n squared plus 15n plus 3 on the right. And if we go a little bit further, but we probably already know that it's going to be, this is true, because on both sides of this inequality, we have the same term. And then we're just adding a few extra positive terms here on the right. So this is clearly true. Because we have that same term that shows up on both sides, and then we're adding a few extra terms there on the right. So the right-hand side of this inequality is clearly larger than the left-hand side. And again, it's because, well, n is greater than or equal to 1. So that's kind of the extra assumption here. For n greater than or equal to 1, that 15n is going to be positive. So it's definitely going to be bigger. All right, so this inequality is true for all n greater than or equal to 1. So not only are our terms positive, well, they also satisfy this inequality, and now we're ready to just state the conclusion. So our series is convergent since sigma bn is convergent by the comparison test. So we just went through. We found our comparable series. We clearly stated that it was convergent, why it was convergent. Then we showed our necessary conditions, and then we clearly stated that the series that we're actually testing here, sigma an, is convergent, and then stated the tests that we actually used. Because again, there's multiple tests that we could be using here. We just so happen to use the comparison test on this one. So we want to state the actual test name. All right, let's try one more. Get a little bit more practice with these. Let's look at example 3. So we're going to determine if this series is convergent or divergent. So here we're looking at the series. We're starting at n equals 0. Again, starting index value doesn't really matter too much for the overall convergence. So we're looking at n equals 0 to infinity of 3 to the n plus 1 over 2 to the n minus 5. We see these terms that are raised to the power n. So that should start looking like this should look like a geometric series. We see constant numbers being raised to the power n. And the only thing that really kind of puts a wrinkle in this is that minus 5. So really it's that minus 5 that is kind of confusing things. So this is going to be our sigma an. This is the test that we don't know. And the first step, if we're going to use the comparison test, is to find our comparable series. And again, the way we can do this is by looking at kind of the dominant terms in both the top and the bottom here. So we're going to do the 3 to the n plus 1 over 2 to the n in the denominator there. And we can see that this is a geometric series. There's maybe a little bit of work here that we need to do to clearly get it into our usual geometric series form. So maybe the one thing we do is we separate off that plus 1 there in the exponent, and then we try to write this as r raised to the power n. So maybe there's a little bit of work here, but we could rewrite this as 3 times 3 over 2 raised to the power n. And now this is clearly in our usual geometric series format, and we can quickly identify the R value. So this is divergent. It's a divergent geometric series. With R equal to 3 over 2. And what happens, how is a geometric series divergent? Well, that happens when the absolute value of R is greater than or equal to 1. So we're just clearly stating what our series sigma Bn is, stating that it's divergent, and then giving a reason. It's a geometric series. We're stating the R value and then the necessary inequality for that R value to give us a divergent geometric series. All right, so we have our comparable series now. Now we want to go through and actually show the conditions. So what are the necessary conditions here for the comparison test? Well, the first one is that we need AN and BN to be all positive. So do we have positive terms here? And it might not be so clear cut here because of this minus 5. So the power of the 3 raised to the n plus 1, that's always positive for n greater than or equal to 0. 2 to the n, that's always positive for n greater than or equal to 0. This minus 5, though, we have a positive number and we're subtracting. That means we might have some negatives. So it's not so clear what's happening here. In our series sigma Bn, everything here clearly is positive. So let's look at what's happening here with this 2 to the n minus 5. Is that greater than 0? Well, that's greater than 0 if and only if 2 to the n is greater than 5. And what is the n value? What power of n gets us bigger than 5? That happens when n is greater than or equal to 3. So once n hits 3, then we're going to be talking about n raised to the power 3 here, which is 8. 8 is definitely bigger than 5. So there's a couple terms there at the beginning, when n is 0, when n is 1, when n is 2, where the terms in our sequence AN are negative, but that's okay. So ultimately what happens here is we do hit a point from 3 onward where our terms AN are all positive. Same thing sigma for BN. All of the terms are positive. So it's okay. We had to go a little bit further into our series, into our terms there, but eventually we do hit a point where then the condition is satisfied. So AN and BN are positive for n greater than or equal to 3. All right, so that's good. Now the other thing we need to show is our necessary inequality. And so we have two choices here. We want to show either AN is less than or equal to BN, or BN is less than or equal to AN. And the which one we use depends on what we think is happening. And so we go up to what sigma BN is doing, and we said it was divergent. So that means we actually want to show this inequality. So this is where BN is, we're adding up the terms, they're getting bigger and bigger. So when we add up the terms for AN, they get bigger and bigger as well. So we're actually going to show this inequality. And again, the one you choose is based on, if we go back to our statement of our comparison test here, let's go back to the original test. We know sigma BN is divergent, so this is the inequality we want to show. So let's go back to the test here, and we're going to show BN is less than or equal to AN. So again, start with what you want and try to simplify it until you get to a point that is clearly true. So let's start with what we want. We want our BN here to be less than or equal to AN. So our bn values are 3 to the n plus 1 over 2 to the n. And we want this to be less than or equal to our an values. So our an values are 2 to the n minus 5 with 3 to the n plus 1 on top. And we know we ran into some issues there with the 2n minus 5. So let's start with n greater than or equal to 3. So if n is greater than or equal to 3, we can multiply both sides of this inequality by 2 to the n, because that's a positive. We can also multiply both sides of the inequality by 2 to the n minus 5, because we know when n is greater than 3, that's a positive value. So we get 3 to the n plus 1 times 2 to the n minus 5 is less than or equal to 3 to the n plus 1 times 2 to the n. And the 3 to the n plus 1s would just cancel. We could divide both sides by that because it's a positive. And dividing by a positive number doesn't change the inequality. So we have 2 to the n minus 5 is less than or equal to 2 to the n. And now we've gotten it to a point where this is clearly true because we have the same value. 2 to the n shows up on both sides. So on the left side, we have 2 to the n minus 5. So we're taking away 5. And on the right side, we have 2 to the n. So the right side here is clearly bigger than the left. So this is clearly true. So once we get down to this point where we have a clearly true statement, it means all of our previous steps must be true, which is actually showing us that the inequality we wanted is true as well. So this is true for n greater than or equal to 3. Again, that's okay. Even though our series here is starting at n equals 0, it's okay. We had to go a few kind of steps in, but eventually this became true. And so then the final step there is to actually kind of state the conclusion. So we've gone through and we've come up with our comparable series. We've shown all the necessary conditions. And so what we want to do is we want to just state the conclusion. So this is the last portion of this. So our original series, the series that we're testing, has to be divergent. And the reason for this is because sigma bn is a divergent geometric series. And we use the comparison test. So the comparison test allows us to kind of state that since sigma bn is divergent, our original series must be divergent as well, specifically because these two conditions are met. All of our terms are positive, and then the appropriate inequality was satisfied. So in this case, we had to show that bn was less than or equal to an. And the way we did that was, start with what you want. So start with what we want, and then simplify that down to a point where you get something that's clearly true. And so you just have to be a little bit careful whenever you multiply both sides of an inequality by a negative, it actually reverses the inequality. So that's why we made this little extra condition here that n was greater than 3 or equal to 3, because this 2n minus 5 does become negative. So when we multiply, in the event that it were negative, we just have to be a little careful here. But setting this requirement that n is greater than 3 means we're okay. 2 to the n minus 5 is positive, so we can multiply both sides of our inequality by it, and it doesn't change the direction of our inequality. All right. So this is really how the comparison test works. Get a comparable series, go through, show the two conditions, everything's positive, show the necessary inequality, and then just write up a nice, clean little statement about why the original series is either convergent or divergent, and state the test that you're using. All right, so that's going to do it for today. Next time, we're going to see there's another comparison test, which we can, is sometimes helpful to use. So sometimes this comparison test, these inequalities get a little tricky. So showing these inequalities can get a little tricky. Sometimes the inequality just isn't satisfied. So it looks like it should, but it just doesn't. So we have this other test, comparison test, which we call the limit comparison test, which kind of allows us to handle those cases where maybe the inequality here is either too difficult to show or it's just not true. So we'll see that next time. So we'll see you then. Bye-bye.